Hey, in this video I'm going to be going over some Bitcoin basics. So we're going to start off with looking at hashing, then blocks, then transactions, and then finally we'll end it off with looking at signatures. Of course, there is a lot of other topics like Merkle trees, Bitcoin scripts, various ways of representing and creating addresses, and there's a bunch of other stuff too that we could look at here, multisig and like TSS, all this stuff. But for this video, we're going to stick to the basics. If this video gets a bunch of views or comments, maybe I'll make another video going over the next steps. But for this video, we'll start off here and I'll work my way through this repo. And along the way, we also have these tests basically to run. And what I recommend you do is you clone this on GitHub. And as we go, it's like here, we're gonna implement this thing. Pause it, try to do it, and then just continue watching the video and you can run the test to make sure it's all good. That's how this is going to work. We're going to go step by step, code this out, and build on top of these things to get something that'll give you an understanding of how Bitcoin worked like in 2009, because there have been a lot of improvements and adjustments over the years. So yeah, that's kind of an intro to what we're going to be doing in this video. So let's get started. So first, we're going to start off with hashing and proof of work. So Bitcoin uses the SHA-256 hash for creating unique block IDs, and for proof of work for mining, which we'll talk about later, and for transaction IDs. So basically, a hash is like, you probably know what a hash is. It's basically like a one-way function where you can't undo the hash and find what the input was. That's basically the main idea. We're gonna just start off with implementing this SHA-256 hash, but we're just gonna use, there's a crypto.create hash. So yeah, exactly what this is here. So this is the type of hash we're using, SHA-256. Yeah, we're just returning basically this like the hash of this data in hex form as well. So that's this part done. Now we're gonna go to proof of work. So mining is basically the block has a bunch of data. So it has like it has data on transactions, data on what was the previous block's hash, etc. Like we'll get into that in a bit. But basically what mining is you brute force trying a bunch of nonces, a bunch of nonce values until the hash of this block becomes below a certain threshold. So it has a certain difficulty level, like for example, needing 4 leading zeros. So in this function, we're basically going to take in the data, which like for now we're just going to call it a string, but later it's going to be the block data to mine. And we're going to input a difficulty. So this is just the number of leading zeros. Alternatively, what's actually used in the real case is like it's not a number of leading zeros, but it's just a hex number, and it gives you a bit more like precision in terms of exactly how much difficulty you want, because you can have yeah, it's just a threshold of like get a nonce that's below this value. We'll implement this mine block. So first we're just gonna set a nonce equal to 0. And we're gonna set the target to this. So this is based on the difficulty. This is how many leading zeros we need, and this is just so we can do an easy comparison in our while loop here. So we're gonna say while true, and we're gonna make a const hash, and this is gonna be a SHA-256 of the data and the nonce. This is just our way of combining it. I guess it is kind of arbitrary because you could put like a space here if you want to, like it really depends, but that's what we're doing for now. And then we're also going to count attempts. I mean, the attempts is literally the nonce plus 1, so you could technically remove this. And then if the hash starts with this amount of zeros, then we'll return this information. So the nonce that works, the hash, like the hash of the whole mined block, and then the number of attempts, and then we also increment the nonce as it goes up. Actually, I'll run the test now so you can see if this is working. Yeah, of course. I need to cd to this. Yeah. Okay, yeah. So our first few work, 1.1 and 1.2. Nice. All right. Next step here. We're gonna go to calculate mining difficulty. So this is kind of a silly function, but I'm just gonna, it's basically for me to explain how it works. So basically Bitcoin adjusts the difficulty every 2016 blocks to maintain 10-minute block times. So what does this mean? It means every 10 minutes a new Bitcoin block is mined on the blockchain, and each of these blocks contains roughly a few thousand transactions, maybe 4,000 transactions. And so if the compute power of the blockchain increases, like there's more people mining, then it's gonna naturally just start mining blocks faster because you have more compute power. But then every 2016 blocks, it adjusts it, and in the case of Bitcoin, it's like the max is like by a factor of 4. So if a ton of new compute power is implemented into mining Bitcoin, is like poured into mining Bitcoin, like at most it will increase the difficulty by 4x to counteract that. But usually it's not going to the extremes, obviously. Usually it's small adjustments to keep it around the 10-minute block times. So here we kind of just have a toy example to pass the test cases, but uh, like here we just have if the actual time is too little, then increase the difficulty. Um, so in this case, we'll just um, like add another 0 is basically what this means. That's what we're counting as difficulty, like add another leading 0, and otherwise do the opposite. So that's basically this toy function, but hopefully that gives you an understanding of what Bitcoin is trying to do with these block times. So next we're gonna verify proof of work. So this is the last function in our hashing section here. So to verify proof of work, we just need to make sure that the hash of the block, if you use the nonce that has been mined, that has been found, actually gets you a hash result that's below the like at the difficulty level, like has that minimum leading 0 amount. So yeah, first we're gonna basically rehash the data in the nonce. So SHA-256 of data plus nonce. And then we're gonna again get our little target thing to make sure it starts with that. And then we're basically gonna return if the rehashed thing that we got equals the hash that was given to us, like when it was mined. If these equal, then that's good. And also it needs to meet the difficulty, obviously. So we also need to verify that. So that's basically done with this. We'll just run it again. But yeah, all of our stuff passes. So yeah, here it's just a little example so you can see as the difficulty grows, like how much more attempts it takes and how much longer it takes to actually mine. So you can see here how it's like difficulty 1 and 2 is very little. It's like 0 milliseconds, and then it grows really fast by a factor of 16 because it's in hexadecimal. So you can see it goes 8 milliseconds, 46 milliseconds, and then 1,000 milliseconds, etc. If you rerun it, it will give you different numbers because this is probabilistic. But yeah, you get the idea. All right, so that's hashing. Next, we'll move on to blocks, and so let's get started. So a blockchain is a linked list of blocks where each block contains the block header. So this is data about the block, the transactions, the data in that block, and it also links to the previous block, the hash. So this is the linked list nature, what makes it a chain. So it's basically an immutable chain, and changing any block in the system breaks all the subsequent blocks because they each link to the previous block using the hash. So that's how you make a blockchain. So yeah, here we just import this from our previous lesson, and then let's create a block. So this function is also very straightforward, just to kind of explain the point. Okay, so there's a few things that we need to create the block. First, we're gonna get the timestamp. So this is gonna be the date.now. Next, we're gonna get the block header. So this is gonna be, yeah, the index. So this is the block number. The timestamp, so the time that this block was created. the data. So this is all the transactions, which we will get to transactions in these last two lessons. And then the previous hash of the previous block, basically. So then we just mine the block. This is the function that we just made. So this basically just brute forces to find the nonce. That's all this does. We just find the nonce here to mine this block. And then we'll return all the information about this block that was created. So we'll just return here the index of the block, the timestamp, the data, the previous block hash, the nonce, the hash. So that's all the information you need from a block. So yeah, now let's come over here and calculate the block hash. So this block hash, what it roughly does is it takes in all the data from the block, including the previous block's hash, and hashes all that in the SHA-256. Well, in Bitcoin, yeah, this is what it contains, what it actually contains in the block header. So it has the version, like the Bitcoin version, the previous hash, the Merkle root. Merkle roots are maybe a topic we'll cover in a separate video, but what it is a way to verify that none of the transactions have been modified, because it's basically a binary tree where it hashes like two things at a time. So it'll hash the first two transactions, it'll hash the next two transactions, etc., and then hash those up and up and up until you have a single hash at the top. So that's what the Merkle root is, and it's a way of thinking of it is it's just a hash of all of the transactions. So if you change any transaction, it's going to mess up the Merkle root. Then we have the timestamp, difficulty, and nonce. And so we'll just simplify it to basically just hashing like this. So we're just going to return the SHA-256 hash of, yeah, exactly what it shows here. So the block.index, block.timestamp, the data, the previous hash, and the nonce. Okay, so now we'll come over to validating a single block. So this is very similar to what we did over here. So yeah, I'll just explain it. So yeah, we calculate the block hash of the block. Which is just this, we just hash it all. And we check if that's the block hash that we were given. So basically we check if it's like the actual hash of these items, and then we also make sure that the difficulty meets the difficulty standard. Next we'll go to validating a blockchain link. So yeah, I'll go one by one here. So we need to make sure that the previous hash matches. So we check if the new block's previous hash is not equal to the previous block's hash, then we'll return false. The next thing we need to check if the new index is not equal to the previous block's index plus 1, then we'll return false, since they obviously increase by 1. And then next, as you can see here, we have the new block timestamp needs to be more than the previous block's timestamp. So if it's not, then we'll return false. Otherwise, we'll return true. So that's how we check for these three things. All right, so now the Genesis block is the first block in the blockchain, and it's special because it has index 0. It has previous hash of 0 since there's no previous blocks, and the data can contain a message. So Bitcoin's Genesis block was this text. This text is actually from a newspaper that came out on around this date, and I guess it's a way of them proving that, you know, it must have come out on at least January 3rd, 2009, because he didn't know of this newspaper any earlier. So yeah, we literally just use the create block function that we made up here. So yeah, exactly this. So we have index, the message, the previous hash, and the difficulty. So that's just using literally the function we just made. And now we're gonna try to make a blockchain. So okay, first we need to get the latest block. So the latest block is gonna be the chain length -1 because it's 0 index, so we have to get chain length -1. and we will get the new block. So we will create a new block using the create new block function that we made up here. And again, yeah, we saw how it works. So we put in the index, we put in the data, and the hash, the previous hash. We don't need to put in the difficulty, it's just set to 4 by default. And we check if this is a valid new block. So this just does these checks that we looked at earlier. The make sure the hash, index, and timestamp all match up as they should. So we make sure that's good, and then we push this to the blockchain, and we just return the new block to show that it's good. So yeah, now we're gonna validate the entire blockchain. So what we want to implement is we want to check that the Genesis block hasn't changed. So the way we do this is, yeah, exactly as Copilot shows. So we check if it's a valid block, and the block is, we input the first block, and the difficulty is whatever difficulty we are given here. It's set to 4 by default, but yeah. So yeah, chain 0 is the first block. So if it's not a valid block, we return false. And now we need to loop through every single block in the blockchain. So we start off from 1, since we've already checked the Genesis block, and we go all the way up to the chain length. So now what we want to do here is check, there's 2 things we got to check. So yeah, validate the block itself by checking if, by using the isValidBlock function that we made with the ith block in the chain, inputting the difficulty, and we also check that it links to the previous block. So we use our isValidNewBlock function we made. I guess you can rename this for clarity to like isValidLink to new to block, isValidLink to new block, or something along those lines. So yeah, we check that as well. And once we've looped through all of them, we just return true since it's all good. All right, so this implements basic system of blocks in the blockchain. We'll quickly run the test to make sure everything is good. And yeah, it all passes. So yeah, this is just a little test of making some blocks and then validating that it's true, and then changing a few things with block 1, and then checking if it's valid, and it returns false. So it's easy to detect when a blockchain is modified. That's what that's trying to show. All right, let's go to transactions. Bitcoin uses unspent transaction output, that's what UTXO means, to model who has how much money. So there's other systems like Ethereum and various other blockchains that use account-based, which has its own advantages and disadvantages, but the Bitcoin model is quite simple. It was the first one made, and basically the way it works is it doesn't store a single number for how much money you have. It basically stores a long list of transactions. Like each block, as I said, stores the 4,000 transactions or whatever it is. And the way you find out how much money you have is you just check how many transactions give money to a wallet public key, or like a wallet address with your address. So how many transactions point to that and are also unspent, because when you spend those, you can't spend them multiple times, obviously. So that's how it finds out how much money a certain account has. So yeah, there's no balances, only unspent outputs. Each transaction consumes inputs and creates outputs. So each transaction takes UTXOs and creates basically new UTXOs. That's how the transaction model works, unspent transaction model. So yeah, inputs reference previous outputs, and yeah, the change goes back to you as a new output. This is not necessarily true, because the inputs need to be greater than the outputs, but any extra inputs go to the miner who mined the block. So that's, I guess, a way of incentivizing your transaction to get processed faster. So yeah, here we just have an example. I'm not going to go over this, but yeah. Okay, so here we want to create a transaction output. All right, the first exercise here is we want to create a transaction output. So the output specifies how much Bitcoin and who can spend it. So yeah, this is just very straightforward. We'll just return it as a single object, the address and the amount. And yeah, it's, similarly, the transaction input is also quite simple. So what we want to specify in an input, it references the previous output, so the transaction ID, which the transaction created the output, the output index, since each transaction has multiple inputs and multiple outputs, and then how much you're using of it, and then who is spending it. So that's all we need in the input. So yeah, just keep in mind that each transaction has multiple inputs and multiple outputs. I want to make sure that's clear. And if you don't spend all of your inputs, since it's kind of like a binary, like spend or not spend, you can create another output that just sends it back to your wallet address. So that's how that works. Okay, now we need to create a transaction. So the transaction consumes inputs and it creates new UTXOs, and it has a unique ID, which is the hash of the transaction data. So we sum the inputs and we make sure that that sum is more than the outputs. And the difference goes to the miners as a fee, as I said a few seconds ago. So we need to create the transaction ID, which is just the hash of the inputs and outputs. So here we use the SHA-256 function that we made earlier, and we use JSON.stringify to stringify this JSON object basically with the inputs and the outputs, since these are arrays. And then we want to return the ID, inputs, outputs, the timestamp, which is the date.now. All right, so now we're going to calculate the transaction fee. I'm not exactly sure if this is super accurate, but so the fee is the total inputs minus the total outputs. So this goes to the miner, as we said. But the way it works in the real world is basically like a marketplace of like transaction fees, and whoever has the highest transaction fee, that's what's incentivized to get put into the newest block by the miners, since the miners want to obviously maximize their profits. So in reality, a lot of wallets and a lot of like systems that are made for users to like buy and sell with like Bitcoin will have something in place to recommend a transaction fee to get your transaction confirmed within a specific amount of time. Generally, people consider 6 blocks, which is 1 hour if you count each block as 10 minutes, to be a safe amount where your transaction is almost certainly confirmed. But yeah, that's basically how that works. What we're doing right here is we just sum all of the inputs, we sum all of the outputs, and we just count the fee as the total in minus total out. So yeah, this is the fee. And we round to 8 decimal places, which is Bitcoin's precision. Yeah, this is another thing that is another trait of each blockchain is the precision. So Bitcoin has 8 precision, Ethereum has 18 precision. Solana has 9 decimal places. I don't actually know if this is true, but yeah, you get the idea. So now we can validate a transaction. So we just need to check all these rules. So it has at least one input and one output. All the amounts must be positive. The sum of the outputs is less than the sum of the inputs, since you can't create money, and the transaction ID must be correct. So I'm just going to paste this in instead of fumbling around here. We'll return true if it's true. So yeah, here we just check what I checked. So first we actually need to check if the inputs length or outputs length is 0, because this is obviously not something we want. And then here we check if the amounts are positive. Here we check if the outputs don't exceed the inputs. So reduce is a way to accumulate an array basically to a single variable, to a single number. So we compare this to the outputs, and then here we just use the SHA-256 function with all of the information in here. So this is just re-verifying the transaction ID. So if all of these pass and nothing returns false, we'll just return true. Now here we are going to make UTXO set. So the UTXO set is a map, and it's used to track unspent transaction outputs. So this is just so that you don't need to query the whole blockchain to find out like which unspent transaction outputs you can use. It's just a way to speed it up. So it's a database of all unspent outputs, and when you process a transaction, you have to remove the inputs from the UTXO set and add new inputs to the UTXO set. So this is how Bitcoin tracks who has how much money basically. So we'll start off with the add here. In this add, we're gonna have a key. So the key that we're using is the transaction ID and then the output index. So these are the two things you need to identify a unique output, a unique UTXO. And in the set, we'll use UTXOs.set. There's a set function on the map in JavaScript with the key and the output. So this just basically is a way of telling it like to add a UTXO with a unique identifier, the key, and we specify the amount here, so it's easy to get. When we remove a UTXO, we just use the map.delete in JavaScript with the unique key, as I've said earlier. And to get a specific UTXO, again, we use the key and we use map.get. To check if it has a specific UTXO, we use the map.has. And then down here, to get a UTXO for a specific address. So what this is useful for is if you have a specific Bitcoin address and you're like, okay, how much money do I have? You can input your address into this function, and this is how it would search through through Bitcoin to see how many UTXOs go to this wallet address. So we're gonna track the result here, and we're gonna loop through all of the UTXO entries. So we're gonna have a const, and this is gonna have a key and the output, and we're gonna loop through all of the UTXOs dot entries. And if the output address equals the address that we've inputted here, we're gonna have we basically split the key at the colon here to get the two values, and then we can add this to the result. So we want to do result.push, and we push the transaction ID and then the output index, which is well, it comes out as a string when we use the key.split. So key is this, and when we use key.split, it gives us two strings, this string and this string. So transaction ID is a string, but then output index is also a string, so we want to parse it as an int, and then the output is just the output here from the UTXO entry. So once we have all this, we return results. So this is an array of all of the transaction IDs, the output index, and all the outputs. So it's an easy way to just locate like what's all the money this address has and where is it, where are the actual transaction outputs. Now we want to see how to make the get balance. So we have our balance as 0, and we basically just loop through all of the UTXO entries. Alright, so the get balance here is just summing up all of the unspent transactions for this address. So similarly to what we did here, except we don't need to actually return an array with all this info. We literally just sum up the output amounts. So that's what this function does. And next, the process a transaction. So this is updating the UTXO set. So if we verify that all the inputs exist in the UTXO set, that's this step here. So we're gonna loop through each of the inputs, and yeah, this should look familiar. We just check if it has it. We want to remove all the consumed inputs. So we delete each of them, and then we add the new inputs. So we set all of them, and then we return true since it's successful and we've processed it. All right, so now we're gonna go to the last section of transactions here. More user-friendly and automatically does all of the steps necessary. So it selects the UTXOs to spend, creates change output if needed, and calculates fee, which again is kind of strange to do here, but yeah, let's get into it. Let's say, so we're gonna build the transaction. So we're gonna get all the UTXOs for this address from. So we're gonna have the const available UTXOs equal to the UTXO set dot get UTXOs for this address. So this is the function we just made above. And we're gonna sort them by amount for smallest first. There's many ways you can do this, but this is one way of doing it. Just sort is by smallest first. We'll say that the fee is, we'll just set the fee to some arbitrary number, like this small constant. But of course, as I was saying, like in the real world, there is some system to find a legit fee that would actually get your transaction in a block within a reasonable amount of time. So the amount that we need in the output is the amount we want to send plus the estimated fee. So that's just what this constant is. And then here we want to select the UTXOs. So the selected UTXOs is just going to be this empty array for now. And we're going to just let the total equal 0 as well. So now we're going to count this up until we reach this amount that we need. So for the constants, for each UTXO, so for each unspent transaction output of the available transaction outputs, we're going to push it to the selected UTXOs, and we're going to increment the total by that output UTXO.output.amount. So if the total exceeds what's needed, we're going to step out of this loop. And first we're going to check, because in some cases we're never going to meet this break statement. We're just going to loop through all of them and then come out. So if the total is less, we're going to throw this error, insufficient funds, since we don't have enough funds for this transaction. The total is not enough. Otherwise, so we're good if we pass this. Here we're gonna create the inputs. So the inputs are, we're basically mapping each unspent transaction output to an input object. So we have this create input way back from here. This create input, from here. So it literally just formats it into this object. That's all this does. Just maps the UTXO into an input object. And then the outputs are gonna be, well, first we need to create an output to the actual to address that we're trying to send it to. So one output's gonna go to there with the amount that we want to send them. And then we have this change, which is the total amount minus the amount that we sent to this new person minus the estimated fee. So if the change is, basically if the change is non-zero, or like if the change exceeds the fee that we have to pay to the miners, then we're gonna push this new output, which will go to ourselves basically. It will go back to our own address since this is extra money in the inputs. So now we can close this and just return create transaction with these inputs and these outputs. So hopefully that's clear. That's how you can create a transaction in Bitcoin. Okay, I just want to quickly discuss the key takeaways at the end of this file, this transactions. So yeah, Bitcoin uses unspent transaction outputs. Each transaction consumes inputs and creates outputs, and the change goes back to you as a new unspent transaction output. So fees incentivize miners to include your transaction in the blockchain in the next block, and if your fee is too low, it may never get included in the next block. If your fee is too high, you might be wasting money and being included in the next block immediately or very quickly, but you might be overpaying. Unspent transaction outputs, the set tracks all the unspent outputs. So basically who has what amount of money, and double spending is prevented by marking UTXOs as spent. So that's kind of what we learned in this section here. Now we're going to move on to signatures. So this is at the heart of how Bitcoin works. So elliptic curve cryptography, or ECDSA, is how we sign transactions in Bitcoin. So we're implementing Bitcoin's cryptography here. So Bitcoin uses this specific elliptic curve, SecP256K1, and the signature algorithm ECDSA, elliptic curve digital signature algorithm. So we're implementing, there's a lot of things going on here, but there's modular arithmetic, elliptic curve point operations, scalar multiplication, key generation, ECDSA signing, ECDSA verification. So we're going to get started off here by just looking at the SecP256K1 curve. On Desmos, we can write y squared equals x cubed plus 7. So elliptic curves generally follow this equation here. Y squared equals x cubed plus ax plus b. So they have these two variables, and when you modify these variables, you get different curves here. So you can see the shape of the curve changes if you change a, and if you change b as well. So what Bitcoin has is it has the specific curve where a is equal to 0 and b is equal to 7. So this blue curve is what Bitcoin uses. All right, so that's the curve that Bitcoin uses. We have this constant setup here with just the parameters that it uses. So P is the prime field. So this is the modulo that we're using. And then here we have A and B, 0 and 7. Then we have the generator point, the base point. So you'll see in a bit where this comes in, but this is just a point on the curve. So this is just a single point somewhere far, 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 like along the curve, if that makes sense. So somewhere far over there. And then we have the order of G, which is the number of points. You'll see where this comes in as well in a sec. So first we want to start off with modular arithmetic. So all operations are done modulo P for coordinates. So here we are just returning A mod M plus M mod M. So this is just because negative numbers sometimes have problems like with modulo, so this just is a way to prevent that, and using big ints. So we're gonna also implement here the mod inverse. So I'll paste it in here. But basically, if you follow these instructions, you'll come out to this. Is basically like, this is an iterative approach to find the mod inverse of with these two inputs. Hopefully it makes sense later. So we're gonna, so this is an elliptic curve point. So this is just gonna store the x and y coordinate. And next we're going to implement other. So this is kind of a big function here. So to implement other, we're going to check, there's a bunch of steps here. Okay, let's quickly go over how point addition works. So point addition in these elliptic curves is basically, let's say you have the point right here. Let's say you have a point here. Basically, if you want to add another point, like add this point for example, you will connect the two with a line, and then you will find where that line intersects again. So I can demonstrate this by using these two things. So let's say this point and this point are the 2 points that you're adding together. You will make a line going through them and then see where it intersects. When you find where it intersects, you will mirror it onto the other side, and then this is your result. That's how you add 2 points. That's how it's defined with these curves and in Bitcoin. The next thing I want to explain is if you want to add a point to itself, let's say you want to add this point to itself, you just take the slope of the line here and then find where it intersects here and then mirror it. So it's a similar idea. It's basically the same thing, but you're finding the slope at that point, since the two points you're adding are like infinitely close to each other. The next point, if you add something at infinity, it's basically just like adding 0. It doesn't change it. So as you can see, if this point is at infinity, return other. And the last thing is, yeah, that should handle all cases actually. So that's all of this stuff here. So I'm just going to paste it in and go line by line explaining it. So first we check if this .x is null, we return other. If other is null, then we return this. So that's just what I said, is basically adding 0. If the points are inverses, so if you try to add this point to this point, the line will be vertical and it will not intersect in a third point. So this is an important edge case here to make sure. We need to check if the x's are equal, but the y's are not equal basically, we return a new point which is just null null 0 0 basically. So that's what we're doing. It's similar to just doing this. If you think about it with normal integers or normal like real numbers, it's just adding the inverse. So that's what that does. Then here there's a formula for the two cases where if the 2 points are along the curve on different spots, or if the 2 points are on the same spot. I'm not going to go over this algorithm. There's a lot of books and videos where you can look at this, but it's basically a formula for P and Q, where P and Q are not the same. You use this setup here. So you calculate this S variable, calculate this X3 and Y3, and then if P and P are the same, point doubling, you use this formula. I'm not going to go over this. It's just there so you know. But that's how you implement this. Next, we want to do scalar multiplication. So we're going to use our addition basically. So we're going to just add it repeatedly. So we start off basically with 0 0. And then we repeatedly set the result to result.add this thing that we're adding. And this this object is what we're adding. So once you add that, like the x times or whatever you're multiplying it by, we just return the result. So we're basically just doing multiplication by using our addition function that we just made up here. And here to check if things are equal, it's just checking if the x So if this dot x is not null and is equal to null and the other x is also null, then we can return true. If either of them are null, so like if one is null and the other is not null, then we return false since they're different. And then here we return if the x is equal to each other and if the y is equal to each other. So to generate a private key in Bitcoin, this gets a little bit interesting. A private key is a random number between that is I believe in Bitcoin it's 256 bits of random data, and that is all the private key is. It's here we use random bytes, so 8 times 32 is 256 bits. We just got random bytes, and our private key is a big int with this hex number of the random bytes. And now to generate the public key, it's just the private key multiplied by g. And g is the generator point that we saw at the top of the file, those two numbers. We just want to multiply, so this is where our multiply function comes in. So we're just gonna get const g as a new point with the two values here, and we just return g dot multiply by the private key. That's how you get a public key. Now we want to sign a message. This is really at the heart of Bitcoin here. So this is like quite a complicated thing to explain initially, but it's when you sign a message, it's basically using ECDSA signing so that you can use your private key to create a number, and people can look at your public key and that number that you made and verify that you actually have the private key when you sign this information, when you sign this message. So nobody else can sign it, only if you have the private key you can sign it. So this sign message function takes in the message hash. So this is just a way to make the message a certain smaller length, so that you're not storing like a lot of outputs or a lot of inputs, and then we have the private key that you're using to sign it with. So this is the whole function here. We basically generate a random k, generate a random private key, so we just use it to generate a random number here. We calculate k times g, and this is r. And then r, the lowercase r is going to be r dot x modded by our n number. And if r is equal to 0, we try again basically. And then we have this k inverse. So we use a modulo inverse with k and this n value to get the k inverse, and then we set s as mod inverse of this k inverse value times z plus r times private key modulo the n value. And then if this is 0 again, we continue and we recompute basically with another random private key. And at the end we return r and s. So these numbers, the main idea here is that we're using this elliptic curve to and we're using a message and a private key to create a signature, and the signature can be verified by other people that have access to the message and the public key. It first converts the hash into a big integer z and defines the elliptic curve point base point g. Then it repeatedly generates a random nonce k, computes the point r equals kg, and derives r and s according to the ECDSA formula. So this is while ensuring neither is 0, neither r or s, and it returns r and s. So r and s are the two numbers that make up the digital signature, and they are publicly shared as the signature. Now we're going to look at how to verify this signature. So I'll just paste this code in, and then explain it. So this code verifies the ECDSA signature, and it first checks that R and S are within the valid range between 0 to n, where n is the curve order. The n is the number at the top of this file that we defined earlier. Then it computes W and uses it to derive like W1 and W2. And then it checks whether the x-coordinate of the resulting point equals r, and if so, the signature is valid. Now we're going to look at generating a key pair. So this just uses the two functions, very straightforward, to generate a public and private key. Now to serialize the public key, this is just the standardized Bitcoin, whether it's compressed or not compressed. So when it's compressed, it just stores the x value basically. Since this curve is symmetrical, you only need to know the x value, and then whether it's positive or negative y to know the y value. So that's all that's needed there. Next we're going to look at creating an address. So we just use our existing functions, the serialized public key, and then we do a double SHA-256 with this serialized to create our address. So this is the address that people can send Bitcoin to. And now we can sign a transaction. So we have the message, which stringifies the transaction information, the inputs and outputs. We have the message hash and then the signature. And we return the transaction and the signature. And now here we can verify transaction signature, and this is similar to what we've done above. We have the message hash, and then we verify the signature, and this is an existing function that, this is just what we made up here. Now we have this create wallet function. So when we create a wallet, we want to have the private and public keys, and then the address to send to, and then for each of these methods to sign, we're going to use our sign message. To verify, we're going to use the verify signature, and then to sign a transaction, we're going to use the sign transaction. So we're basically all done here. I'll just run the tests. So yeah, we're all done here. So this has been making Bitcoin from scratch.